Hello friends, here is a sneak peek into our biology and bioengineering summer camp. In this summer camp, we will learn about biology and bioengineering for 21st century. Let us meet our guest speaker, Nikhiya Shamsher, who is going to participate in the summer camp. Nikhiya is currently a first-year undergraduate student at Stanford University studying biomedical computation. Nikhiya has been conducting research on oral cancer for over 4 years. Nikhiya developed a biochemical test for cancer risk evaluation that she named QuitPuff. Her invention got the third grand award at Intel ICEF 2019 fair. What is QuitPuff? QuitPuff is a low-cost, point-of-care, non-invasive test for early risk detection of oral precancer and oral squamous cell carcinoma. It is a simple home-based test costing just Rs 38. All it requires is 1 ml of saliva that needs to be mixed with the QuitPuff reagent. How does it work? Well, the color change in the mixture of the QuitPuff reagent on addition of saliva is matched with the colorimetric lipid peroxidation index chart to interpret the degree of lipid peroxidation in the saliva. This indicates the level of risk. You would be amazed to know QuitPuff was tested on 500 subjects from 3 hospitals and has an accuracy rate of 96%. We are all excited to hear from Nikhiya. Let's listen to what Nikhiya herself has to say about the summer camp.
Hi, my name is Nikhiya. I was the third grand award winner in biochemistry at Intel ICEF 2019, and I'm currently a student at Stanford University. I'll see you at the biology summer camp.
All right, so welcome Nikhiya here. So I'm sure all of you will be happy to see her as a young scientist, young achiever, who is of your age and going to speak to you about some of the work done by her and her future vision and future plan. Nikhiya, over to you now.
Thank you so much, sir. Thank you so much for the introduction. Hey everybody. I'm really excited to be here and talk to you. I'm going to start sharing my screen now and going through the work I've done. And then maybe at the end, if there are any questions, we can go through that. Or I'll share with you my email ID and you can contact me there. So what my research is about is, I've called it QuitPuff. It's a point-of-care diagnostic for early risk detection of oral precancer and cancer in chronic smokers. So it's basically a test that you can do yourself. It's super simple. You can do it at home, and it'll tell you your risk of developing oral precancer and cancer. So, but before I go into the test and how it works, it would be useful to examine why the test is even important, or why any early risk detection test is important. So, in India, India basically has the highest incidence of oral cancer, and it accounts for 1/3 of the entire world's cases, which is a huge amount. We have a huge population, but still, these many people getting sick is terrible. Then, over 5 people die every hour, which is a very, very high mortality rate. And the main reason for this high mortality rate is late diagnosis, which sounds quite, when you first hear it, it sounds quite silly. Why is something like late diagnosis affecting people so much? And why is late diagnosis still a thing? Now, the reason for that is because there are lack of labs in rural areas. So people who live far from the cities, they have a really hard time getting tested. And because they can't spend a whole day traveling far into the city to get tested, they end up going way too late when they have a huge bulging ulcer that they cannot bear anymore, or they cannot work anymore because of it. And by that time, it's already too late. So The other issue is lack of education. People don't know that this is something that this is something that's important. They don't know that they can fall sick, or they can fall terribly sick, and they don't know that they need to go and get tested, or that there is an availability for tests like these. Then they don't have the time. A lot of people are daily wage earners. A lot of people in rural areas are daily wage earners, like farmers. If they take out a whole day to go to a hospital and get tested, and tests like these don't end in one day, it ends up being a week-long affair, their families don't eat for that day, or their families don't eat for that week, which is why they simply can't afford to take out time from their day and go to a hospital and get tested. So now, another reason why late diagnosis is so important, or is such a big issue that we have to solve, is because at stage 1, there's an 80% chance of survival. But just a little bit later, at stage 3, the survival rate reduces to 20%, which is incredibly low. And this can happen over the course of a couple of months, which is why we really need some sort of early detection method. So how I started out was I saw this issue and I thought, okay, let me Google and see what tests are currently there. And I didn't find anything that was simple and home-based. Everything I found was a lab-based test. And again, as we discussed, there aren't labs in rural areas. So there are a lot of people who don't find this accessible, who can't, who don't have access to labs, and who can't get these tests done. There needs to be something that's simple and home-based, something that can be stored easily, something that can be transported easily, and can be given to people easily without needing a lab tech or someone who knows how to administer the test. It needs to be done by anyone and everyone. And I found out that unfortunately something like this doesn't exist yet. And that's what I set out to work on. So now let's get to the actual technical stuff. So what the principle of the test is, it works on something called malondialdehyde, which is a biomarker for oral precancer or cancer. Now, a lot of studies have shown that there is an increase in MDA concentration in all the stages of oral precancer and cancer, and also before that in chronic smokers. So these are the papers, in case you're interested. These are the names of the authors. And all of them show that salivary malondialdehyde from the saliva could be used as a diagnostic marker. So now, if you want to go into more detail about how much MDA malondialdehyde is present in saliva. In oral precancer stages, it's reported to it has been reported that it's at 25 to 50 nanograms per ml, and in oral squamous cell carcinoma from 50 to 100 nanograms per ml. So after this, I went through a lot of different methods. I went through a lot of different papers, and I saw how they detect MDA. And it basically works with another chemical called thiobarbituric acid. And these thiobarbituric acid and malondialdehyde react, and they produce a result that's colored. But the issue is, it doesn't. A colored result isn't present when malondialdehyde concentrations are really, really low, something as low as 5 nanograms per ml. But in the human body, you do get values of malondialdehyde as low as 5 nanograms per ml. So these tests still need a lab, because after the color change occurs, you need lab equipment to detect the color change, because the color change is so little. So what I worked on was coming up with basically a formula that works, that will detect malondialdehyde, will give visible color change at levels even as low as 5 nanograms per ml. So after a lot of research, after trying out a bunch of different methods, I have 10 listed here, but there were a lot more. And all of these I looked at other papers, I modified theirs, I tried to learn from them, and that's how I came up with my own formulation. It detects malondialdehyde levels as low as 5 nanograms per ml by producing a visible clear color change. And if you're interested, this is what the reagent consists of. I call it thiobarbituric reagent, or the quid puff reagent. Now, thing is, my invention is a test, which means I need to know what the color change will be like for certain malondialdehyde levels, and I have to test it out on patients where I won't know their malondialdehyde levels. So I need to make a standard, which is what this section is about. I took the saliva of 10 people, and I took 10 ml of the saliva, which took time, of course, and I sent the saliva to a lab to get tested, and I ensured that there was no malondialdehyde present before any testing. Then I went ahead and added known amounts of malondialdehyde. So with serial dilution, I created 7, one was a control, where I had varying levels of malondialdehyde. So it went from 500 nanograms per ml to 250 to 100 to 50 to 25 to 5. And these I call the MDA standards. I did this 10 times. So you have 1A, B, C, D to F, and then 2, 3, 4, 5, all the way to 10, A to F. And a control after that. So after this, I took 1 ml of this 1 ml of the MDA standard, added 2 ml with the control, added 2 ml of the thiobarbiturate acid reagent or the quid puff reagent. I heated it in a water bath for 15 minutes, and then I recorded the color change. And this is what the color change turned out to be. So 1A, which had the highest amount of malondialdehyde present, it ended up being the darkest. And F, which had the lowest amount of malondialdehyde present, ended up being lightest. And the color change and the blank or the control remained, had no color change. So there was a clear gradient that was observed, and this was observed in all 10 of the samples. So this allowed me to sort of create a basis, a standard that I can compare to when I test, and I don't know what the malondialdehyde levels are. So with that, I sent these samples to a lab for UV visible spectroscopy, and this is the curve I came up with all the values. This is the curve I came up with. But the issue is, a curve like this still isn't user friendly. If you went and showed this graph to someone, to a random person, chances are they wouldn't understand what's going on because again, it's not user friendly. And the point of the test is to make it as user friendly as possible. So I took this curve, I took all my readings, and I came up with a lipid peroxidation index chart, which is a color-based chart. This is something that's easy. After you do the test, you just have to match the color to this chart, and you can figure out what your level of lipid peroxidation is and what your level of risk is. So you can see 0 is very little, 1 is low, 2 to 3 is moderate, and 5 to 6 is high. So after this, I had to test it out on 500 subjects where I didn't know the malondialdehyde levels. So I got an ethics approval from the Institutional Ethics Committee, which is very important because if you're ever dealing with people, you have to get an ethics approval, even if it's something as small as getting their saliva and it doesn't damage them in any way. You have to get it, and you have to get informed consent from every single person, preferably informed written consent. So these 500 subjects, they came from 5 different categories. So the first category was non-smokers. These are people who had no history of smoking. They did not have any average tar content inhaled or eaten in a day, and no comorbidities. The next group was smokers who smoked less than 10 cigarettes a day, but had no oral lesions, no comorbidities. The third group was smokers who smoked between 10 to 20 cigarettes a day, but still had no oral lesions, no comorbidities. Fourth group was people who smoked more than 20 cigarettes a day, again, but with no oral lesions or comorbidities. And the fifth group was finally with people who were recently diagnosed with oral precancer or cancer, but hadn't started their treatment yet. And there were different types of oral precancer. So oral erosive lichen planus, oral leukoplakia, submucous fibrosis, and then oral squamous cell carcinoma. So these were the different categories, and the reason I tested over so many different categories is to first of all, why there were so many smokers who had no oral lesions, no comorbidities, is because the test is to detect your risk of developing cancer. It's to help you catch cancer before you even get it. It's not it's not a diagnostic tool. It's not to tell you you have cancer, but it's to prevent it. That's why the research was so focused on people who hadn't developed cancer yet, and who were at different stages of possibly developing cancer. So again, I did the same thing. I added 1 ml of their saliva. I added 2 ml of the thiobarbituric acid reagent, or the quit-puff reagent. I heated it for 15 minutes, and then I observed the color change and matched it to the lipid peroxidation colorimetric chart. And with that, I recorded all of the data. And this is sort of a summary of it, of the average lipid peroxidation index across the different groups, and the p-value, which basically which is quite low, which basically says that the results are statistically highly significant, which is good. That's what you'd want. It says that your results are very viable. They're good. They're useful. So this is another table with a little more information. After I got the LPI through my method, the lipid peroxidation index through my method, I sent all the samples to a lab for UV spectroscopy, because I use that as my validation. And if you can see the amounts right now, I'll just point them out. Just a second. So all the amounts are quite close to each other, but again, quite close is not a very good scientific term. So I ran Spearman's correlation, and I found that there is significant positive association between the color change and through the UV through my method and through the UV spectroscopy method. And this is what the R value turned out to be. So coming to the conclusion, 20 out of 500 were results misclassified, which means that the result I got from my method and the result from the UV spectroscopy method did not match. So there was a 4% issue, and that resulted in my test having an accuracy of 96%, which is still something I'm working on and trying to improve right now. This is an overview of the other tests that are available. And the features that they have, and why, and specifically here are the features I included that I think are very, very important, that need to be included in a test that that's supposed to be for early risk detection, is supposed to be accessible, it's supposed to be for everyone, and can be done by everyone. So obviously point of care, home based, something that's quick. People aren't going to invest in a test that takes 2-3 days, or most people won't. To get it as accessible as possible to as many people as possible, it has to be quick. It needs to be stored and transported easily. So it needs to be able to be stored at room temperature, somewhere far, far away. It needs to be okay if it's transported somewhere far away and takes 2-3 days in transportation. It needs to be cheap, because people are not going to spend a lot of money on something on something they aren't particularly curious on learning about. If they were willing to spend the money, they would have just gone to a hospital. But a lot of people aren't willing to spend the money, and a lot of people can't afford to spend the money. So you have to make it as accessible for them, and that's why the cost has to be low. And another thing that's quite useful is something that can be used as a mass screening tool, something that you can have a huge crowd hopefully after COVID, a huge crowd of 1,000 people and get all of them tested in 1 or 2 days. It needs to be used quickly and with a large population. So some quick things I think would be useful to discuss. The test, it detects risk at a very early stage, which is what is important. Not at a very early stage of cancer, but a very early stage of smoking, a very early stage before cancer, which is what, if you are planning on making a test for early risk diagnosis or for prevention, that is something that's very important. That's something that your test has to have. It has to have potential of reducing morbidity. It has to be able to save people. It needs to be something simple, do it yourself, home based, which I already spoke about. It has to be something that people can do themselves. Something as simple as something as how a pregnancy test is so simple and it's so accessible. You can go to a store and easily buy it. And so people can use it more easily. They can do it themselves at home. And it doesn't involve any fear of going to a hospital or time or affordability. It needs to be very easily accessible. It needs to be available everywhere. So it cannot be, it doesn't have to be stored at very difficult temperatures or very high temperatures or very low temperatures, or have be stored at a certain pressure or something like that. That would make it not very accessible. It needs to be sold at pharmacies or at supermarkets, something like that. And of course, it needs to be affordable. So this is what the test looks like if you're interested. This is where the thiobarbituric acid reagent is. That's a container for you to spit in, and that's a dropper for you to take the saliva and put it into the tube. And moving on, what I'm currently working on right now is I'm working at the Felcher lab at my university, Stanford, and we're working on the MYC oncogene and seeing how closely involved it is with cancer pathways and how its inactivation can lead to tumor regression. So if you have any questions about QuitPuff or any research or just anything really, this is my email ID down here. You can always reach out. I'll be happy to answer any questions now, or if you'd like to email them. And lastly, there are just a few people I'd like to thank. And most importantly, I'd like to thank Professor Srivastava for this incredible opportunity. And I hope you guys learned something. And I'd love to answer any questions.
Great, Nikhiya, wonderful work. Congratulations. And you can see in the chat box, lot of applause for you from the audience, from the students. So you have really paid attention to very minute details, and especially how to make it more affordable and for the mass screening. So wonderful work done, and wish you good luck to take this forward for the mass screening. Due to the shortage of time, we have to restrict to the questions. Please look into chat box, and